In last video we talked about feed forward. In this video we will discuss backpropagation. Backpropagation is to adjust slightly weight and bias values to find the optimum representation of the classification. There is one user-defined variable learning rate, which determines how fast we going to adjust weights and biases. We use an algorithm called gradient descent to do this. The basic intuition behind gradient descent can be illustrated by a hypothetical scenario. A person is stuck in the mountains and is trying to get down. There is heavy fog such that visibility is extremely low. Therefore, the path down the mountain is not visible, so they must use local information to find the minimum. They can use the method of gradient descent, which involves looking at the steepness of the hill at their current position, then proceeding in the direction with the steepest descent. If they were trying to find the top of the mountain, then they would proceed in the direction of steepest ascent. Using this method, they would eventually find their way down the mountain or possibly get stuck in some hole, like a mountain lake. The gradient of h at a point is a plane vector pointing in the direction of the steepest slope or grade at that point. The steepness of the slope at that point is given by the magnitude of the gradient vector. To minimize the cost function, we have to update weight values such that the cost decreases. To do so, we need to take the derivative of the cost function with respect to each weight. We start from output layer and call this phase 1. So the left side is the derivative d cost divided by d weight output. It equals the formula on the right, which involves output node value before softmax normalization. If we apply derivative calculation on the first two parts on right side, it is equal to output value minus target value, which is the label value. The third part on right side is equal to output from previous nodes. We will not go into details of how we calculate derivative, this can be found on internet. Now we have the derivative of cost and weight. Next one is to find derivative of cost and bias. Similarly, the left side is the derivative d cost divided by d bias output, on the right hand side. For the first two parts, we already know is equal to output value minus label value. The third element on right side is the derivative of d output value divided by d bias value. This is equal to 1. So now we have both derivatives for cost weight and cost bias. We can multiply them with learning rate to adjust all output weights and biases for output nodes. After understanding the theory, the implementation is not so complicated. Let's move to coding. First, we assign label values to target values. Current value set is calculated from feed forward codes above, is equal to self.ao. We then get the learning rate from view class, and turn it into a float number. Similar to feed forward, we need a loop to go through all nodes layer by layer. But this time we travel backwards from output layer first. Inside the loop, we first start from phase 1, which is the output layer. The d cost d0 represents first two parts on right of the equation, which equals current value minus target value. The third part on right side of the equation equals to output from previous layer, which we can get from the list we put in during feed forward. By using these two, we apply the multiply function from number pi to these two lists. So we got the deviation for weight. We collect unchanged weights to be used in phase 2. After that we can apply learning rate with deviation to modify all current weights. We do the same for biases, we need to use some function to get a number instead of a list. where d cost by BO is just equal to d cost by DZO, and is just a list of current value minus target value. Now we can look into phase 2 of propagation within the else statement. Now we are into phase 2, backpropagation for hidden layers. Similar to phase 1, we need to calculate the deviation for d oxt versus d weight hidden. The formula is similar, and we can break it into several parts. The first part on right can be break into multiply of difference between current and target values and weight of next node. The second part on right is the derivative of sigmoid function. And third part on right is equal to previous node output value. For biases derivative, let's look at the third element on right side, dzh divided by dbh is equal to 1. Where the other parts can be borrowed from weight derivative calculation. Now we can look into the overall process. We travel the nodes layer by layer, where we also need to use weight on next layer and output from previous layer to complete the adjustment of weights and biases. When we are going backwards to first layer, we then will use the input training feature data as previous output to complete the process. Now we go to coding part. DZO divided by DAH equals to unchanged weights from next layer, which we have saved in phase 1. D cost divided by DAH equals to multiply of current and target value difference and weights from next layer. And then we calculate the middle part on right, the derivative of sigmoid function. We also need to create this derivative of sigmoid method. Then we need to check if we have reached the input layer. If so, we use training feature data as previous input. Otherwise we just retrieve the output value we saved in feed forward phase. We turn these data into DZH by DWH, now we have all the components required to work out backpropagation. The cost weight derivative equals to the multiply of 3 parts on right we calculated above. The cost bias derivative equals to multiply of 2 parts on right as the last one is 1. After that we assign d cost bias hidden to d cost DZO, as they are the same thing. We need to use d cost DZO in next round calculation. It presents the difference between current and target value of a node. We save current weights here for next round calculation. Finally we can apply learning rate to derivatives and modify weights and biases accordingly. This will complete train loop method in controller class. Now, it is time for testing. We create more nodes to see how it goes. It is running fine, and cost function value is decreasing, means the network is adjusting to the data set and become more accurate. The status bar is showing time spent as well as percentage of training completed. The core logic of a neural network is completed, and in next video we will learn how to save and load networks so we can reuse them for prediction. Thank you for watching. If you like this video, please thumb up. Please subscribe for upcoming interesting videos. If you have any questions, please feel free to post as comments.